Okay. No more linear algebra review. It's the real stuff. I have chalk to write it down. Okay. Now, of course, in any branch of numerical analysis, you're always trying to quantify error, for instance. We're dealing with vectors and matrices, so we need some way of describing the magnitude of a vector or matrix using a single number, and that's what norms are for. So first they're going to cover various ways of getting the norm or magnitude of a vector, and then we'll move on to matrices. Okay. So basically what vector norms do, or any kind of norms do, is generalize magnitude and also distance. If you have objects that make sense to subtract, certainly vectors and matrices fall in that category. This gives you the notion of the distance between vectors and then later matrices. And we want to make sure that vector norm is a natural generalization of absolute values. So that we're going to deal with vectors of a general length n, but if n is 1, then these norms should reduce to absolute value. So a function that's denoted by using the double vertical bars, and then the dot here is just a placeholder. So that's where we're going to be evaluating this function at. So from of course, everything I'm going to talk about is going to apply to generalize a natural way to complex vectors, but we'll work with a real vector space. The function is mapping n-dimensional vectors into the real numbers. And in order for such a function to be called a norm, it has to have these three properties. So first, the norm of any vector can never be negative. Doesn't make sense to have a negative magnitude. And the norm is 0 if and only if x itself is the 0 vector. All right. Second, if you are scaling a vector and then you take the norm of it, that's exactly the same as just taking the norm of the vector itself and then multiplying it by the magnitude in this, or absolute value of the scalar. Okay. If this were complex, then we'd be talking about complex modulus in this case. And so you're all familiar with triangle inequality. That the norm of a sum is less than or equal to the sum of the norms. Okay. And certainly if n equals 1, then of course the absolute value would satisfy all of these. Okay. Now, what are some vector norms that we can use? Well, at least one of these you're definitely going to be familiar with. So ones we're going to use called p-norms. So it's a whole family of norms that can be all defined in a common way. That the p-norm of a vector x is, you take the absolute value, or complex modulus as it were, of each of the components, raise it to the p power, sum them all up, and then raise that to the 1 over p power. So, so for any number p, you can define it this way. Now, they're also referred to, I think is what I use in the notes, the LP norms. So some books prefer to use that term. But there are certain p-values in particular. Okay, I definitely don't mean p-values in statistics. Certain values of p that are of interest. So the 1 norm, so if we just fill in p equal 1, then we use the sum of the absolute values. Okay. And then p equals 2. So that's a 2 norm, but they also know it as the Euclidean norm because this is how we compute the magnitude of a vector in Euclidean space. The distance formula that you would have seen in calculus number of classes is this exact one. So the 2 norm is just the square root of the sum of squares. It may seem redundant to take the absolute value, but I'm covering myself for like the complex case where we really do want the complex modulus or absolute value, I guess, squared. And then what we can also do is take the limit of this as p goes to infinity. Because what happens is the larger the value of p, the more emphasis the largest component of a vector is going to get. So when the limit as p goes to infinity, it becomes totally dominant. So the infinity norm is just the magnitude or absolute value of the largest component of a vector. So as an example, if this was my vector, I can compute norm in any of these ways, and of course the values are all going to be different. So for instance, the 1 norm, let's sum the absolute values. And we're going to get 6. If we take the 2 norm, so square root of, okay, so we get the square root of 14 in this case. So it's going to be certainly smaller, since the square root of 14 is going to be like 3 point something. And then finally, the infinity norm of this vector is going to be what?
3.
Yeah. So it's just the absolute value of the largest component in magnitude 3. So yeah, so what's interesting is that as you increase p, generally this is not universally true, but the norm tends to decrease. But it's because of how you're balancing the weight of each of these components that the lesser components make less of a contribution to the norm as p increases. Okay. Now, this. Those of you who haven't taught yet will experience this, and those of you who have been teaching may experience over if it's ready. You see what you're going to cover that day or at a particular juncture, and you're like, oh, this. even if you enjoy the topic overall. I have this proof I need to do, and I actually don't like the proof in the notes. So I'm not going to do that. I can provide a different proof, though. That's, to me anyway, much more appealing. And I think simpler to digest. Okay. Okay. All right. Now, so one inequality that certain vector norms satisfy is the Hellder inequality, which says that you have two n vectors, you take their inner product and take the absolute value, that it is less than or equal to p norm of x times the q norm of y, where the norms p and q satisfy 1 over q equals 1. So I should mention, p is not required to be an integer, because you can use anything as an exponent, any real number. Now, vector norms, in general, the norms for vector spaces, including vector spaces such as Rn, generalize in a natural way to norms for function spaces. So you can define p norms for function spaces, where instead of a sum, you're using an integral. And in that case, I've actually used a norm with a negative value of p. It was what I needed at the time. Now, one special case of interest, when p and q are both equal to 2, certainly that would satisfy that. And this is commonly referred to as the Cauchy-Schwarz inequality. One textbook I saw added a third name, Bunyakovsky. Only seen it once, though. So apparently, poor Bunyakovsky got the shaft. But a lot of things like this end up being discovered independently. Now, so this states that the absolute value of the product is less than or equal to a product of the Euclidean norms, or two norms, the vectors multiplied together. Okay, so for a proof of this, so if I consider the 2 norm of this vector, so alpha is just any scalar, and I'm going to square it. Now, because it's the norm, it's certainly non-negative. Now, I should mention that, actually I should have mentioned this over there, that, so I'll just put it here, the 2 norm, or Euclidean norm of a vector can be written in terms of an inner product. All it is, so the equivalent of a formula over there, is just the square root of the inner product of a vector with itself. If it's a real vector. If it's a complex vector, I need to be a little more careful. I need to use the Hermitian transpose. So that's what you need for inner product in that case. Okay. And so with that in mind, it's funny how when you're going through a sequence of steps like this, some authors or professors, like since I'm going to write something that's going to be equal to this, would put it equals here. But the majority I've seen say that what you put here should be related to this. What I'm putting here is maybe equal to this, but it's also greater than or equal to 0. So I'm going to follow that convention, even though what I can put here will equal this. So I can write this as the inner product. I'm going to assume everything is real here. This vector x plus alpha y itself, just by squaring both sides of that formula for the 2 norm. And then, using properties of the dot or inner product, I can express this as x transpose x plus 2 alpha x transpose y plus alpha squared y transpose y. Because when the vectors are real, the dot product is commutative. I have y transpose x and x transpose y, but I can combine those terms. So we have this quantity that is non-negative. But now what I want to do is find the minimum. So if I think of this as a function of alpha, then to find out where it's a minimum, I can take a derivative. So g prime of alpha would be, well, I get nothing from this term because there's no alpha in it, so the derivative of that part is 0. Here I would get 2 x transpose y, and then 2 alpha and y transpose y is the same as the 2 norm of y squared, so I'm going to need that later. And then I can go ahead and set this equals 0. I just realized I probably should have put minus, but since alpha is an arbitrary real number, I think it'll turn out okay. Let's find out. So now I can just go ahead and solve this for alpha. What is alpha?
Minus norm of y squared over, let's see,
You got that? Not
No.
quite.
no?
No.
Oops, sorry.
What's
It's
the
minus x transpose y over y.
Yeah.
Y
squared.
Yeah.
Yeah, over the 2 norm of y.
Yes. Yeah. Sorry, what were you asking?
Oh, I couldn't, it's a 2 in front of the alpha, right?
Yeah.
Okay.
Yeah.
I couldn't quite make it out.
Okay. Yeah. All right. So yes. So it's minus. The 2's will cancel. So x transpose y over norm of y, 2 norm of y squared. Okay. So now what I can do, so this is a quadratic function of alpha. So it's going to have a, and since the coefficient, the coefficient for the quadratic term, being y transpose y, is positive, and it should. Let's be more precise. I'm going to put assumptions in here that these vectors are non-zero. If the vectors were 0, then of course this would be trivially true. But yeah, I definitely need y to be non-zero for this. So this is a quadratic function alpha. It has a unique minimum, so we could have just done it in a more college algebra-like way, like finding a vertex of a parabola, but whatever on that. So now I can put this value of alpha in here. So, so minimum of g of alpha turns out to be okay, x transpose x, but that's the 2 norm of x squared. And then I plug in this value of alpha here, so I have minus 2 x transpose y squared, because I have 1 from here and 1 from here, all over 2 norm of y squared, plus, so now I have this x transpose y squared, and then I have 2 norm of y squared, and now I'm going to have down below 2 norm of y squared squared, so 2 norm of y to the 4th, but of course this is going to simplify. And because this came about as the norm of some vector, all of this is still non-negative. So to finish this off, so now what I have is 2 norm of x squared minus 2 inner product squared over 2 norm of y squared plus inner product squared, and then I simplify the various powers of norms of y that we have there. And these terms combine so then all I have to do is rearrange this and take the square root of both sides, and the Cauchy-Bunyakovsky-Schwarz inequality falls out from there. So everything works out, and we call it good. Okay. So, nothing to it. Okay. Now, so one helpful thing, and this will be important when we, especially when we talk about, for instance, iterative methods for solving systems of linear equations, we can use vector norms to describe what it means for a sequence of vectors to converge. Because if you're doing a sequence of numbers, then we have like our epsilon k definition from like real analysis to describe that. So generalized to vectors, we can use a norm. So, so the distance between two vectors x and y, we can just select some norm, and just take the norm of x minus y. And so based on that, we can say that a sequence of vectors, xk, actually I'll use a notation in my notes, because often I'll use a subscript to refer to a component of a vector. So if I want to index the vectors themselves, I'll use a superscript here. So if I have a sequence of vectors, say x1, x2, and so forth, going all the way to infinity, we can say converges to a limit x if, so we can describe this in terms of an ordinary limit of a sequence of numbers. So the norm of the difference, norm of the distance between xk and x goes to 0, then we say it converges. Okay. And for a particular problem, it should be specified what norm is being used. Now, now using the properties of norms, though, since this is converting to a zero vector, convergence is happening if and only if each component of xk is converging to the corresponding component of x. I can't write anymore. Okay. So component-wise convergence is the same thing as convergence of the vector as a whole. Okay. And that's because of the first property of norms, that the only way the norm of a vector can be zero is if the vector itself is a zero vector. So all of the components of this difference must be going to zero. Okay. Now, one nice thing about all these norms, though, is you don't want to have a situation where a sequence of vectors converges to a limit in one choice of norm, like a 1 norm over 2 norm, and then fails to converge in another. But generally that doesn't happen. I mean, the actual norms that you're getting will be different, but if one sequence of norms is going to zero, then others will too. So here would be a very important concept of norm equivalence. So two norms, like the alpha norm, the beta norm, are said to be equivalent if there are certain constants, C1 and C2, that are independent of x, such that the beta norm of x is bounded above by C2 times the alpha norm, and is bounded below by C1 times the alpha norm. So this is something that is true for all x in the vector space under consideration. Then the two norms are equivalent. So the sequence on the convergence of one norm will definitely converge in the other. Whoops. That should be an alpha, not an infinity. Right, so we're saying the alpha and beta norms are equivalent. Okay. And for the norms that we've been talking about, here are some specific examples. So in fact, one blanket statement I can make, all P norms are equivalent. But here are some specific relations between the norms we are most interested in. So you can say that the one norm is greater than or equal to the two norm for all x. And this is less than or equal to the square root of n times the two norm of x. So to get an idea of how these relationships can come about, like for instance, can these inequalities become an equality? Suppose the vector x has only one non-zero component. Then any norm of that vector, any p norm of that vector, is just going to be the absolute value of that component. So these two norms would be equal. But another case that's worth looking at is suppose the vector has all components equal. Like for instance, every component is equal to 1. So if x is equal to a vector consisting of all ones, then what that means is the p norm, what's going to happen is you're going to add up 1 n times, and then you're going to take the take that to the 1 over p power. So the p norm of this vector is n to the 1 over p. So in other words, the 2 norm is going to be square root of n. The 1 norm is just going to be n. So this relationship, this inequality, becomes an equality in that case. All right? And those are good boundary cases to consider. If a vector has only one non-zero component, or if it has all components being equal. All right, so that's one example. A second example relates the 2 norm to the infinity norm. So the infinity norm is less than or equal to the 2 norm. It has less than or equal to square root of n times the infinity norm. And then finally, a relationship between the 1 norm and infinity norm. All right, so the 1 norm is greater or equal to the infinity norm. So actually, the statement that I said was generally true is, I should have checked myself there, but it's actually always true that as p increases, the norm of x is going to be at least non-increasing. Because all components with the largest start to get less and less emphasis. Okay, this is less than or equal to n times the infinity norm. So if we go for example, suppose x has all components equal to 1. Then the 1 norm will be equal to n, but the infinity norm will only be equal to 1. So that's when this relationship becomes an equality. Okay, so this is just to ensure that whether a sequence of vectors converges is independent of the norm being used to define convergence. Okay. All right. Okay. So I want to, again, these first relationships here. I wanted to prove these. Okay. Okay. So I want to prove that the 2 norm is less than or equal to the 1 norm. Okay. So, okay. Now, it's helpful to look at these norms squared, because the 2 norm x squared is the sum of squares for all components. On the other hand, the 1 norm squared so I'm going to take this whole sum and square it. That's going to be a double sum of xi times xj. So here we are taking all possible products of elements or absolute values for all I and j going from 1 to n. These terms are some of the terms in here because this is a case where I equals j. So in fact, I could write this as a case where I equals j, where it's squared, plus the sum where I is not equal to j. But this is exactly the 2 norm squared. So since the 1 norm squared is the 2 norm squared plus some other stuff that's going to be non-negative, that's how we can prove that the 2 norm is less than or equal to the 1 norm. And then for the other side of the equivalence relation, to prove that the 1 norm is less than or equal to square root of n times the 2 norm. So what I can do is I can define a vector y I'll define a component y as follows. So each component is equal to 1 if xi is positive, and minus 1, alright, so not negative, and then it's negative, I'll set it equal to minus 1. That's supposed to be 0, not some random blob. What that means is the 1 norm, which is a sum of the absolute values, but that's the same as saying it's a sum of all the positive components plus the negatives of all the negative components. So in fact, I can write this as x transpose y. So that's just another way of expressing the 1 norm. But by the Cauchy-Schwarz inequality, this is less than or equal to norm of x times the norm of y. But y, all the components are plus or minus 1. And this norm is the square root of n. So the relationship falls out from that. Okay. So any questions about these norm equivalence relations? All right. Now, that's vector norms. Now we'll shift gears to matrix norms. Really want to be able to measure the magnitude of a matrix. Okay. So a function that maps all m by n real matrices into real numbers has to have similar properties. That norm is always non-negative. Norm is 0 if and only if the matrix is 0. Scaling has to work in the same way. And also a triangle inequality. Now, another property that textbooks don't necessarily include in the definition of a matrix norm. So for property with a question mark. And technically, this property applies not just to a single matrix norm, unless you're talking about square matrices, but actually norms for matrices of different sizes. This is called the sum-multiplicative property, and it turned out a very important one. That says that the norm of a product of matrices is less than or equal to the product of the norms. But like for instance, if A is m by n and B is n by p, so AB is m by p. So we're talking about really three different matrix norms if these dimensions are all different. Okay. But often it's square matrices where we need to use this, or the case where A is a matrix and B is a vector. That's particularly useful for that. Now, how can we get matrix norms? Most common way of defining a matrix norm is to be induced by a vector norm. So we define the induced norm it's also called a natural norm. We define a matrix norm in terms of a appropriate corresponding vector norm. So it's equal to the supremum over, okay, so A is m by n. So we consider all n vectors must be non-zero. And we take the supremum of this quantity, the vector norm of AX over the norm of X. So actually we're dealing with two different vector norms too. One for Rm and the other of the numerator, and then normally use the denominators for Rn. So we still are using the same general vector norm for both cases. So we just take a supremum of this quantity over all non-zero vectors, and that is the value of our matrix norm. Another way of describing it is we take the maximum over all vectors whose vector norm is equal to 1, and then we just look at AX. Sometimes this one is more convenient. Okay. By the way, can anyone tell me why, in the first case, I have to say supremum. I cannot necessarily say maximum, whereas in the other case I can. Why does it matter?
Because we don't know if the numerator has the maximum dimension or the denominator.
It's really more like a real analysis point. The set of all vectors with a norm of 1 is a compact set. Continuous function in a compact set is guaranteed to have a maximum and a minimum. So we could say this set has function restricted to this set has a maximum. This is not a compact set. It's consisting of all vectors except for the 0 vector. So it's actually an open set. It may or may not have a maximum, so we can't be certain. It may have a situation where it's approaching some maximum in the limit. So just to be careful, we put supremum there instead. Okay. All right. See if I can get from these pages before we end. All right. Now, and I should mention all matrix norms that are induced by P norms or LP norms can be shown that they satisfy this fourth property here, the submultiplicative property. Okay, so that's something we can take advantage of. And almost all matrix norms we're going to use are induced norms. So just one I need to show you that's not. Okay. Now, what are some specific matrix norms? They come from the vector norms that we're talking about. So we have the one norm. So the one norm of a matrix A. So the way it's defined is the maximum over all vectors whose one norm is equal to 1, and we take the one norm of A times X. Now the thing is, that's not very convenient. We need it's not like vector norms where we have an explicit formula for the norm of any vector X. Trying to take its maximum would be a real pain. But fortunately, we can obtain a formula for a one norm, and that's what I'll do now. So what I need to do is, I need to find an upper bound for this. And then I need to show that, to confirm that this upper bound is like the least upper bound or maximum, I need to find an x which makes this inequality an equality. So the one over AX is defined to be the sum of the absolute values of all the components of A times X. Now A is an m by n matrix, so AX is a vector in Rm. But now I can fill in the formula for matrix vector product. Alright, so this is equal to, so inside this absolute value, I'll have a sum, j equals 1 to n, of aij xj. Now, we're assuming that x has a one norm of 1. So that means that the sum of all the components of x is equal to 1. And we're going to use that later. So by the triangle inequality for absolute value, I can say this is less than or equal to, and I'm going to move the sums around, because for some reason in these proofs it's always necessary. Reversal of sums seems to be a key step. Then I equals 1 to m of absolute value of aij times xj. All right. Now, okay. So I'd like to get an upper bound for this that has nothing to do with x, but I need to take advantage of the fact that the sum of all of these is equal to 1. So what I can do is, because this inner sum here is that's a column sum. I'm taking the sum of the absolute values of all the entries in column J, and then multiplying that by xj. Now, okay, before I continue, can choose capital J. Be the column in which the maximum of all these column sums occurs. So, alright, so this is equal to the maximum of all column sums. Okay. So now what I can do is I can say that the norm of AX, one norm of AX, is less than or equal to and now I have, so before I had AI little j, but now I can have AI big J, and then I still have xj. But now, this expression on the inside, in parentheses, doesn't depend on little j anymore. I can pull it out. But this is equal to what? Because we're only taking value expression over all vectors x whose one norm is equal to 1. So now we have an upper bound. It's the maximum column sum. So now we know that the one norm of A, the matrix one norm of A, is less than or equal to that. But now I'd like to show that this actually is equal. So if I let x equal to E capital J, okay, actually, yeah. And that means that AX is going to be the capital J column of A. It's going to be A1 capital J, A2 capital J, AM capital J. And that means that the one norm of AX is going to be equal to some of the absolute values of all these components. So it's equal to this upper bound. So, so that proves that that is the one norm of A. So the one norm of A is the maximum column sum. Keep in mind that we're taking some of the absolute values of the entries. Don't forget to do that. Any questions about that proof? Okay, so that's one of the matrix norms of interest. Now I'll give a few more. Okay. The infinity norm so that's defined as the maximum over all vectors whose largest component has an absolute value of 1, AX, infinity norm. And there's a formula for that too. It's actually the maximum row sum. So as a result, what you can say is the one norm of A is equal to the infinity norm of the transpose. Alright, so at least those norms are easy to compute. Unfortunately, the same cannot be said for the 2 norm. Alright, so we have our definition that we take a maximum over all vectors of unit Euclidean length. So all vectors, all points on the n-dimensional unit sphere. Okay. Now, let's see. I may not have time to get into the details of it here, but if I define the function g of x to be this, okay, because I can also say that this is the soup over all non-zero vectors, 2 norm of ax over 2 norm of x. So if I define this way, I'd like to find the supreme of this function, or maximum if it has one. And this can be written as x transpose A transpose AX over x transpose x. So what I could do is try to take the gradient of this function and see where it's equal to 0. And
Excuse me.
yeah.
Why 2 norm is not a compact set?
Well,
It's a closed set, isn't it? Isn't it the circle?
well, yeah, the unit sphere of it is a compact. That's why I could compact. That's why I could take a maximum in this case. But here, I'm taking all non-zero vectors. But that restriction, max versus soup, that applies to any norm. It's not specific to the 2 norm. Yeah. So the gradient of G, we can use something along the lines of the quotient rule. So it's just a straightforward generalization of that. So we have x transpose x times the gradient of this. And actually, at the end of a review, give a formula for the gradient. Okay, so in general, for gradient of x transpose ax is x transpose is a plus a transpose times x. Well, A transpose A, that was the matrix that we have here, that is a symmetric matrix. So what we end up getting is 2 A transpose A x. Okay. Minus x transpose A transpose AX times the gradient of x transpose x, which is 2x, all over x transpose x squared. And what we could do is, I'm going to factor out a 1 over, actually a 2 over x transpose x. And what's left is A transpose AX minus, and what's left is x transpose A transpose AX over x transpose x, which is a number, all times x. And we want this to be equal to 0 in order to have any hope of finding a local maximum or minimum. And when you have a matrix times a vector equal to a scalar times a vector, so the local max or min if if x is an eigenvector of A transpose A. And then the eigenvalue which actually is equal to value of g of x. Okay. Now, A transpose A, okay. Because these expressions are always going to be positive for and it's only defined for non-zero x. Okay. All right. So the okay. So that is how we can. So we can take the largest of these, and that's going to be the absolute maximum. So we could say that the 2 norm of A, since our function g came from the square of norm of ax over norm of x, so it is the square root of the maximum eigenvalue. And I'll talk more about eigenvalues in the next class. Square root of the largest eigenvalue of A transpose A. Later we'll talk about singular values. So it's actually saying it's a singular value of A. Okay. Unfortunately, that's not so easy to compute. So the 1 norm and infinity norm are far easier to compute than the 2 norms. So it's often not a good idea to use this in practice. Well, it's certainly good for analysis. Okay. And then finally, one more matrix norm. This is actually not an induced norm. The Frobenius norm, so it's an unnatural norm, if you will. And we use the capital F to indicate this norm. So this is the square root of the sum of squares of the absolute values of all the entries of a matrix. Okay. So in fact, you might think that maybe this is what the 2 norm was supposed to be. But nope, it's a Frobenius norm. So in fact, if you took the matrix and reshaped it into a big long vector of length m times n, and took the 2 norm of that, that would give you the Frobenius norm. So that's going to be useful in various cases for analysis. But it's also something that's pretty easy to compute. Similar to the effort involved with the 1 norm and infinity norm. Okay. Let's see, how am I doing on time? Oh, good. I'm not going to be behind. Okay. Now, just as you have equivalence among vector norms, you can have equivalence of matrix norms too.
Excuse me, what do you mean by not natural?
Oh, it's not induced by any vector norm. So there's no connection. Or like 1 norm, infinity norm, 2 norm, they were all defined in terms of their corresponding vector norms. So we say they're natural or induced by those vector norms. But Frobenius norm is in a category by itself. Okay. It's funny, I'm always writing like, from Frobenius norm of A, we're always using a generic matrix A. And only more recently does this make me think of how AF is used in normal lingo. So I didn't think I would when I first learned about this stuff back in the 90s. So, so for equivalence, of matrix norm, so the Frobenius norm is greater than or equal to the 2 norm, less than or equal to square root of n times the 2 norm. Okay, the 2 norm compared to the infinity norm, the relationship's a little more complicated because I'm dealing with matrices. So it's greater or equal to 1 over square root of n times the infinity norm, less than or equal to square root of m times the infinity norm. And then, if I just reverse the roles of m and n, I get relationships between the 2 norm and the 1 norm, because the infinity norm of A is the 1 norm of A transpose, whereas the 2 norm of A equals the 2 norm of A transpose. So then I have 1 over square root of n here, and square root of n here. All right. So as an example, if I have, for instance, okay, so we compute some norms of this matrix. So keep in mind the formulas we came up with for, like, what would the 1 norm of this matrix be?
7.
Yeah, it's the maximum column sum. We go down to columns. We get column sums of 2, 3, and 7. Okay. What about the infinity norm?
6.
Yeah, because the first row has the largest row sum. And the only other one we can compute is a little more work, but the Frobenius norm. Okay, so we're going to have 1 4 9 is 14, 15, 16. So it'll be the square root of 32. So, wait. 4 times the square root of 2. Okay, so no surprise that the 1 norm is larger, well, actually, yeah, but you can't really expect, if I take a transpose of this, then these would be reversed. So you don't have the same relationship with vector norms as you do with matrix norms as far as that decreasing as p increases. Okay, so 4 squared root of 2, that's roughly like 5.6 or so. Now, unfortunately, it would not be so easy to compute the 2 norm of this matrix. So now the you can compute the so if you want to compute norms in MATLAB, so you can do the norm of A. That is the 2 norm by default, and you can specify other norms. Like for instance, this is true for a vector or a matrix. So you can do just so if you want to use a different p, you can just specify that as an argument. Now for other norms, you can also do the infinity norm. So you put I and f in quotes. And finally, for the Frobenius norm, you put fro in quotes, single quotes. And so that's how you compute the various norms that we talked about today in MATLAB or Octave. So if I'm using, like for instance, that's an iterative method, I want to measure error, but using some norm. Generally, I'm not going to use the 2 norm. I will for a vector. It's fine to use it for that. But otherwise, it'd be best to use like the infinity norm over the over one norm. Least amount of computational effort. For matrices, they're doing comparisons, but that's better than like a floating point arithmetic operation. Okay. All right. Questions? Yeah. Even though we're beyond the linear algebra review, it's still kind of preliminary, but we're getting there. So, towards slowly towards more interesting stuff. Okay. Yeah, I brought notes for the next section just in case, but you know what? I think we're going to call it good. Only 3 minutes to go. So, okay. Well, also we're missing people, so okay.